Class, today's topic is discrete Fourier transform or DFT. So let's proceed with the topic. Before we move to the definition of DFT, we want to recollect what was DTFT, that is discrete time Fourier transform. Discrete time Fourier transform was applicable for both finite and infinite sequences. If you remember the formula for DTFT, it was x of e to the power j omega was equal to summation n going from minus infinity to plus infinity x of n e to the power minus j omega n, just to make you recollect. Now, if you come back here and see the formula for DFT, you find the symbolic representation of DFT is x of k is equal to summation n going from 0 to n minus 1, capital N minus 1, x of n wn to the power kn. So what we notice here is the limits of the summation has changed from 0 to capital N minus 1, previously which was minus infinity to infinity in the case of DTFT. That means we can say that DFT holds only for finite sequences, unlike DTFT, which was for both finite or infinite sequences. Here the limits are limited to 0 to n minus 1, that is, the length of the sequence always has to be capital N. Now, if we go back to DTFT and put the limits as 0 to n minus 1 in DTFT, what we get, if we expand the equation, what we get is x of 0 plus x of 1 e to the power minus j omega plus x of 2 e to the power minus 2j omega plus x of 3 e to the power minus 3j omega. In this way, it will move to x of n minus 1 e to the power minus n minus 1 j omega. That means we can say that in DFT, we have capital N pieces of information, which when are collected together, we get DFT. That is, what we are doing is we are sampling DTFT in frequency domain, or we can say we are sampling DTFT in equally spaced, the space is capital N, we are sampling DTFT, or we are sampling DTFT in frequencies domain to get our DFT. Or we can say that equally spaced frequency samples of DTFT is DFT. That means we are sampling DTFT into n different informations. If we break x of ej omega from 0 to n minus 1, we will have 9, or we will have capital N pieces of information. This is what is DFT. That is, we are sampling the frequency spectrum of DTFT into n pieces. That is, what is happening to omega here? We know in DTFT, omega was from 0 to 2 pi, or we can say the omega ranged from 0 to 2 pi. Now if we break omega, the frequency, into n pieces, so each angle will be twice pi by capital N into twice pi by capital N into what? Into k, where k goes from 0 to n minus 1. Each angle will be twice pi by n into, I am repeating, each angle will be twice pi by n into k, where k goes from 0 to n minus 1. The first angle will be 0, then the twice pi by 1 by n, then will be 2 into twice pi by n. In this way the angles will be sampled. So in the equation of dtft, if we put the limits as 0 to n minus 1 and omega is broken into e to the power minus j omega, here omega is twice pi by capital N into k. So what we will be getting is, if you note carefully, what we will be getting is our x of k, that is the equation for DFT. Now the new term here is Wn. If you notice, what is Wn? I have mentioned here, Wn is equal to, W suffix n is equal to e to the power minus j twice pi by n, which I was talking about. So in the equation of dtft, we have replaced the limits and we have replaced omega by twice pi by n, and everything remains the same, and what we get is our DFT. Now e to the power minus j twice pi by n has gone into the literature as Tweedle factor, W suffix n. It is the symbolic representation and is called as Tweedle factor. So in the equation of DFT, we have replaced e to the power minus j twice pi by n by W suffix n. Now the inverse DFT is given by x of n 1 by capital N summation n k going from 0 to n minus 1 x of k Wn to the power minus kn. See, if you want to find the similarity between DTFT and DFT equations, you will find that in DTFT there was a negative sign in power of e to the power minus j omega n in the equation of DFT and in the DTFT, and in the equation of inverse DTFT there was a plus sign. Here it is just the opposite. You have a power Wn to the power plus kn in DFT, and in IDFT you have a minus power, because Wn itself has absorbed a negative power e to the power minus j twice pi by n. The proof of this inverse DFT you will get in books. I am not going into the proof of the inverse DFT. So we move to the next slide. That is properties of DFT. So if we take two signals g of n and small h of n, and if you take n point DFT of these two signals, which is coming up to capital G of k and capital H of k, then the properties are: number 1, linearity. As we all have seen in the previous transformation methods, the first property which is common to all the transformation method is linearity property. Here also we have the same linearity property, which is if we multiply Gn with the scalar quantity alpha and Hn with the scalar quantity beta and add both of them, and then if we take n-point DFT of this whole signal, that is alpha Gn plus beta Hn, what we get is alpha multiplied by the individual DFT of Gn, that is Gk, plus beta multiplied by the individual DFT of Hn, that is h of k, capital H of k. This is the linearity property which we have proved several times, and the method remains the same, and I leave it to you all. So now next is circular shift. In order to make you explain circular shift, a lot of time will be required and the video length will be increased. So I leave it here today, and in the next class we will move to circular shift, and I will explain what this phenomena is, because this term is new to you all. So we will be meeting in the Google Meet session and solve if any doubts for today's class. Thank you, class.